Okay, next slide. Given the name, you should be able to write the formula. There you go. With the ion table in your hand, as it says there. Well, there's ionic compounds that are made of ions, and the only thing that holds those ions together is the attraction of opposite charges. Opposites attract. There's another type of molecule that actually consists of atoms connected by chemical bonds. A chemical bond is a physical connection, kind of like a stick. It's analogous to a stick between two Tinker toys. A chemical bond consists of a pair of electrons. Don't worry about what the electrons are doing. And we just show a chemical bond with a dash. Like, I'm showing some 3 chemical bonds up there. Carbon-hydrogen bond, a nitrogen-hydrogen bond, and an oxygen-hydrogen bond that I'm going to talk about in a while. Okay. So there's ionic compounds which are highly polar and dissolve in water, and there's always a pair of names like sodium chloride or calcium sulfate. Then these covalent compounds are named totally differently. Like this one here, a carbon with 4 hydrogens connected to it, has the name methane. Maybe you've heard of methane. It's the primary component of natural gas. And we write the structure of the molecule like that over there, using dashes to show chemical bonds. So what I want you to know is, given the formula, I may ask you to write a couple of simple structures like that. I'll give you the formula, and you write the structure that actually shows what's hooked on to what. I'll give you some examples.
So you give us,
I give you the formula like
okay.
H2O.
H2O, okay, yeah.
Okay, so if I give you H2O, that tells you what atoms of what type are in the molecule, but it doesn't really tell you what is hooked to what. Okay. First thing though, you've got to know the bonding rules for these simple, just these. I want you to know the bonding rules for oxygen. Oxygen always has 2 chemical bonds. Nitrogen always has 3. Hydrogen always has 1. And carbon always has 4. Okay, so you can see, and those are the only ones you got to know. You can see that this structure over here obeys the bonding rules for carbon and hydrogen, doesn't it? Because every hydrogen has 1 bond, and the carbon has 4. Can you see that that obeys the bonding rules? Mm-hmm. Suppose I gave you the formula C2H6O. Just for instance, okay, and asked you to draw, a valid structure for that. There might be more than one you could draw. Okay, every different structure that you can draw represents a different substance. Okay, so the point is, you want to draw a structure, and I'm not telling you what structure to draw as long as it obeys the bonding rules. These are the bonding rules, okay? And every carbon has to have 4 things hooked onto it. So you want to bring a pencil with a good eraser to this quiz. Please don't do it in red pen or any kind of pen, okay? Have a pencil with a brand new eraser on it, not an old one that is really gross and stuff you never use and it doesn't work. So anyway, let's draw a carbon with 4 things and let's start filling them in. Well, we got 6 hydrogens to work with and 2 carbons to work with. So I could write another carbon over here, and that would use up my 2 carbons, and every carbon's got to have 4 things hooked onto it. I could start using up hydrogens. 1, 2, 3, 4, 5. What do I still have to go?
Oxygen.
I have an oxygen. Have I used all my hydrogens?
No.
No, I got one of those too. And so that would make sense, wouldn't it? And that's a real structure. That is the molecular formula for ethyl alcohol, the active ingredient in alcohol beverages. Okay. Are there any other ones you could draw that have that formula?
Yeah.
Yeah, there's another one. What if you put the oxygen in the middle instead of on the end? Okay, you could write a formula that obeys the bonding rules. And so and I will only ask you a molecule that has those atoms in it, okay? So put the oxygen in the middle, and you can draw a sensible molecule. It's kind of fun. This is a totally different substance. It's a gas, and it's nothing like ethyl alcohol. In fact, it's poisonous. A poisonous gas called dimethyl ether, and highly flammable, to almost to the point of being explosive, and toxic. Really nasty stuff. I've worked with a lot of bad things. I don't think I've ever worked with that one. I've worked with worse things than this. But, okay. So, that's an example of,
Valent bond.
yeah, I give you the formula and you write the structure of the molecule. So you'll get one of those too. Want me to do any more?
Can we do one more?
One more? What about,
Huh? Makes it better.
how about one that just has carbon? Oh, let's write, I wonder if I can do one with, let's try one like this. I might outsmart myself here. Let's see if this one will work. Okay. See if I can make a sensible molecule out of that. A C2H6, well, that's not, let's try C3H8. Make it a little more interesting. So, since I got 3 carbons now, one interesting thing to do might be to, what if I hooked 3 in a circle? You've got these bonding rules written down?
Yes.
Okay, 1, 2, 3. And what if I had that? And so I've used up 5 hydrogens. And what if, and we have a nitrogen coming off here. And
Oxygen.
so I've still got an oxygen to go. I've only got 1, 2, okay, I've got 4 bonds there, 4 bonds.
What about between the two of the hydrogens?
So, you could also, yeah, like you say, Tony, you could cheat, do that. And so I've still got 1. The problem though is,
Three.
oh, I know what I could do. You could have double bonds. That's a pretty exotic compound, but it obeys the bonding rule. I wonder if it's ever been made.
Aren't you missing
what-
2?
Okay, 1, 2,
hydrogens?
3, 1, 2. No, this has 5 bonds to carbon here. That won't work. Okay, and so 1, 2, 3, 4, 5, 6, 7. No, that won't work. I need to have 8. And so it all comes back to me now. that anytime you stick a nitrogen in it, you've gotta have an odd number of hydrogens. Okay? And so if I gave you that one, it would work. That's a pretty exotic compound.
Would it have propyl in the name?
Oh,
Yeah.
that would be so hard to name.
Yeah.
Yeah, I could name it. I'm not sure you wanna hear the name of it. It's a cyclopropane derivative. Yeah. 2-amino-2-hydroxyl cyclopropane. So. So, I won't ever give you one like that. Like the previous example. Okay? Did that help, or did that just make it worse? Okay, so, but you'll get us a couple simple ones. Well, I could give you one just with carbon and hydrogen. Like, why don't you try for a homework problem, why don't you try C3H8? Okay, and then try C4H10O2.
See what?
C4H10O2. So those should both work. C4H10O2 should work.
So when you do it, for like C3H8.
So every carbon's gotta have,
Do we have to put the H actually on, or can we just put the line?
oh, do you have to show all the H's? You're asking. Can I get lazy and not show all the H's? Well, I'll only give you a couple. It's not like you're doing 30 of them.
Well, cause you don't always have to put the chemistry, right?
If I were asking a whole bunch of them, I'd say, just draw a line and I'd know that there was a hydrogen on the end, but
Okay.
if I, just for a couple of them, geez. Okay, so covalent compounds don't possess all the charge that ionic compounds have. Ionic compounds, because of their high degree of charge, are all highly polar and dissolve in water. Okay. Highly polar molecules, remember the word polar? It is so important in biological systems. It explains so many things, like likes dissolve likes. The kidneys only eliminate polar substances, blah, blah, blah. These ionic compound or covalent compounds possess much less charge. Some of them possess no charge. Some of them possess a little bit of charge. Okay, next slide. So this is a slide I want you to understand completely. It shows water molecules interacting with each other. Okay. And the water molecules could be shown like this. They're bent, and it turns out that anytime you have an OH bond, that the oxygen and the hydrogen have a fraction of a charge on them, called a partial charge. And the fraction is just indicated, believe it or not, this is a lowercase Greek delta. Don't ask me why they settled on that, but this little squiggly means partial. It means some fraction of a charge. In the case of the OH bond, it's quite a large fraction of a charge. Okay? It's not as much charge as if you had ions, but the amount of charge character possessed by water, because of this, is responsible for most of the properties of water. It's the reason why water molecules have so much attraction for each other, and the kind of attraction that we're talking about is very important in nature, because it's quite common to have OH bonds and NH bonds in nature. And so when one water molecule sees another water molecule, they align themselves like this, so that, remember, opposites attract, so that the partial negative end of one molecule is very close to the partial positive end of another molecule. Okay, and we use this dotted line to indicate attraction. Okay, and this is a very special kind of attraction where one of the atoms is hydrogen, because hydrogen is very small, and so the molecules can get very close together, thus optimizing this attraction. And this special kind of attraction is called hydrogen bonding. This picture, you should really know everything about this picture. It says hydrogen bonding between water molecules. All water molecules are polar, of course, because they're all the same. But water molecules are very polar because of this partial charge character. Because all a water molecule has is OH bonds, isn't it? So there are two OH bonds for every water molecule. And so the water exhibits the classical example of hydrogen bonding. Hydrogen bonding is the force that holds the twin strands of DNA together. So it's really important in nature. I mean, the twin strands can be pulled apart. So I never cared for the term hydrogen bonding because it's not a real chemical bond. It should be called hydrogen attraction then. Because you can unzip a DNA molecule. It's a strong amount of attraction, but it can be pulled apart, and that's what happens when a gene is expressed. Okay? So, but it's the reason why water evaporates so slowly. It's the reason why water is a liquid that has a high boiling point, and it's easy to freeze because of the strong attraction between the molecules. Okay? And it can dissolve ions, which most liquids can't, because ions have a super amount of charge character, but you get a whole bunch of water molecules in one place, and they're very small, so you can get a lot of them in one place. You got a lot of charge that's capable of stabilizing dissolved ions. So that's why ions dissolve in water, see? And so water and ions have a unique relationship in biological systems. Next slide. So that is one of the most important slides. A partial charge is a fraction of a charge. Okay? And I showed you the two important examples. A carbon-hydrogen bond doesn't have those charges. And so molecules that only have carbon-hydrogen bonds don't have that charge character. Thus, the molecules don't exhibit that attraction for each other. Okay? And so hydrocarbons, a gasoline is a mixture of 500 different hydrocarbons that contain only carbon and hydrogen. So none of the atoms in a hydrocarbon molecule possess this partial charge character. So does gasoline behave like a substance that has a high degree of attraction between the particles?
No.
No, it's a very volatile liquid that evaporates very readily, and it would be a real bear to freeze. You'd have to make it way cold to freeze it, and it evaporates really quickly, and that kind of thing. And would it dissolve ions? No. Ions wouldn't get within a mile of hydrocarbon liquid, any hydrocarbon liquid. And so these hydrocarbons, the smallest ones are gases like natural gas, methane, you know. And with only 4 carbons, you get up to butane. That's a gas, isn't it? Well, it's a gas. Propane and butane have 3 and 4 carbons. They're liquids when you pressurize them, but if you take the pressure off, they turn into a gas, don't they? They're easy to liquefy, and that's which is convenient, because we use propane and butane liquid, but it's the gas that we actually burn. So when you open the spigot, it lets the pressure off and converts back to a gas. But the 1 and 2 carbon form are gases at room temperature, and natural gas is just 1 carbon, methane. So, a molecule can either be described as highly polar, moderately polar, or nonpolar, depending on the amount of charge character it has. Okay? And ions are highly polar. They're the classical example of highly polar substances. Water is the classical example of moderately polar. Alcohol, anything that's got an OH or an NH bond in it. Remember, alcohol had an OH bond in it. So there are degrees of moderately polar. I mean, water for something we would call moderately polar is really pretty highly polar. So, and all hydrocarbons are your classical nonpolar substances. Hydrocarbons have only carbon and hydrogen. It's because, sugars have a whole bunch of OH bonds in them. That's why they're solids. Okay? And they act almost like ions, don't they? They dissolve limitlessly in water because of that hydrogen bonding that can exist between all those OHs and all the OHs in water. I mean, you can only dissolve so much salt in water and it'll start to pile up on the bottom. But you can dissolve an almost limitless amount of sugar in water because of that hydrogen bonding that can exist until you get to a syrup, look at honey is, carbohydrate dissolved in water, and there's about 95% solid dissolved in just a little bit of water, and it'll crystallize if you leave the top off, and that water evaporates out of there. So, and syrup you can't make a syrup out of ions like you can out of carbohydrates that have all those OHs, and it's because of hydrogen bonding. Next slide, please. And so water molecules have such a high degree of attraction that the surface of water acts like a skin, so that light insects can float on it. And we talk about the so-called surface tension. It's because of hydrogen bonding at the surface. The attraction between those water molecules on the surface that gives it that property. Pour a beaker full of acetone and see how long those bugs will float on it. Not very long. They'll sink like a stone. Okay. So, and capillary action is the same thing. Next slide. Okay. So what determines whether something is a liquid, solid, or gas is how much attraction the particles have for each other. I used to have a demonstration I'd do where I had a glass tray full of BBs, and I would set it on an overhead projector, and it had a glass bottom. And so I would illustrate a solid by tilting it to one side and not moving it. And in a solid, all the particles are touching, and they are in a rigid crystalline structure so that the particles always have the same neighbors. Okay? In a liquid, they acquire more energy. You can melt a solid so that it becomes a liquid by putting energy into it, and they get the particles vibrating, and they'll overcome the attraction enough so that they still are right next to each other, but they're free to roll past each other. They don't have the same neighbors anymore. And I would illustrate that by tilting the tray back and forth, but holding it tilted to one side. Okay? And in a gas, you have to boil a liquid to get gas, and so you get so much kinetic energy in there that the particles overcome any attraction they have for each other and fly out. And in a gas, the particles are banging around with the wall of the container and again with each other, and they're moving so fast that even if they have attraction for each other, they don't stick. However, the more charge character they have, the easier it is to condense them back to a liquid like water. You can take water vapor like in a cloud, and it comes up against the side of a mountain, and it cools the cloud off, and that slows the particles down. Temperature is a measure of kinetic energy. And if you slow those particles down enough that when they hit each other, they'll start to stick together. If they don't have any charge character, it doesn't matter if they hit each other or not. If how slow they're going, they won't want to stick together unless you practically stop them, and then they'll finally turn into a liquid. So, okay, so it's a matter of polarity. Non-polar substances tend to be gases like oxygen and carbon dioxide. But non-polar substances also tend not to dissolve in water very readily. Okay? And in a liquid, the particles are all touching each other, but they're free to roll past each other. Okay? And they still have a fair amount of energy. In a solid, you're in a rigid crystalline situation where the particles always have the same neighbors and are frozen into a particular crystalline configuration, whatever that might be. And things that solidify easily are more the highly polar things that have a high degree of attraction, crystallize easily. If they are moderately polar, they'll have a moderate amount of attraction, and they'll tend to exist as liquids at room temperature. Okay. And if they're nonpolar, they'll have very little attraction, and they'll tend to be gases at room temperature. Okay. Units of gas pressure, we talked about that. It's convenient for us to use millimeters of mercury. And if you take a big long tube and fill it full of mercury, it's open at one end, hold your finger over, turn it upside down, put it in a dish of mercury, it'll run down a little bit, but it doesn't run completely out because the atmosphere is pushing down. Doesn't seem like much of a push to us, but it's pushing down on the dish, which converts to an upward push that holds the mercury up in the tube. And to the tune of 760 millimeters of mercury at sea level. So we're really experiencing quite a bit of force from just the weight of the atmosphere. If you think about it, there's a lot of atmosphere on top of us. It's heavy, and it weighs on us.
So one atmosphere weighs 700.
One atmosphere is equal to 760
Okay.
millimeters of pressure.
Okay.
This is a convenient unit because it goes to zero when the pressure goes to zero. You like to have units that are zero when the thing you're measuring is non-existent anymore. And so the units are directly proportional to the magnitude of what it is that we're measuring. So the entire scientific community uses millimeters of mercury. Next slide. Okay. Dalton's law of partial pressure merely says that in a mixture of gases, the total pressure of the mixture, and of course, if we're talking about air, the total pressure is going to be 760 in Brookings, isn't it? And so if you took each one of the gases out and measured its pressure separately, and wrote it down, all the numbers would add up to 760. Okay? And nitrogen, it's 21% oxygen, so if you took 21% of 760, you get 159. And most of the remainder in the atmosphere is due to nitrogen. So it's 601, I think, comes out to be, with just a trace of carbon dioxide and a trace of water. You get inside our lungs, and the amount of water vapor and carbon dioxide are much greater. Next slide. So we see that in our lungs, we no longer have 159 millimeters of mercury because, or we don't have 601 millimeters of nitrogen because some of the pressure is taken up by the partial pressure of hot water vapor and the partial pressure of CO2. Water vapor is a gas that obeys gas laws. So all those add up to 760 though, still. What do you think that the partial pressure of oxygen is in the Chetco River? Go to the next slide. Henry's law. When a gas sample is placed over a liquid, the amount of gas which dissolves in the liquid is directly proportional to the pressure of the gas sample.
So it must be 760.
Okay. And so, what's the partial pressure of oxygen? I mean, the fish don't care about the nitrogen. The fish only care about the oxygen. So what's PO2 in the Chetco River? What's PO2 in the atmosphere?
or,
Where's the Chico River?
PO,
oh,
well,
wouldn't
Chaco
know,
River
so-
isn't on here. Back a look again,
that,
there you go,
Right
no,
there?
no,
Oh.
next one.
okay,
So the PO2 in the atmosphere is 159, so
Okay.
what's the PO2 in the Chetco River gonna be?
159?
159,
yeah.
okay? So, you're not gonna find Chetco River on there, unfortunately. But, but in the lung, it's 105, and that should become a familiar number to us in lecture.
Do we just need to know like 760 and the partial?
Yeah, 105. And Henry's law is very important. It's, we use partial pressures to express the concentration of dissolved gas. It may seem a little bit strange to use a pressure to express the concentration of a solute dissolved in water. But if that solute is a gas, it does make sense. If the partial pressure ever gets up to 760, the gas will come fizzing out of the water. Think of nitrogen. Partial pressure of nitrogen is 601 at 1 atmosphere. And so suppose you're 200 feet below the surface of the ocean and you're breathing your air at a pressure of 5 atmospheres. Then the PN2, the partial pressure of nitrogen, will be 5 times 600, will be 3,000 millimeters of mercury. Can you see how, as you start to ascend up to lower pressures, that the PN2 would very quickly become less than the pressure of whatever pressure was holding it in solution? And Lord forbid if you came right up to the top and you had a PN2 of 3,000 in your blood, and the PN2 in the atmosphere was only 602, that gas would come explosively fizzing out of your blood all over your body, with doing tremendous damage to your capillaries. And,
Because we can only retain a certain amount of oxygen at a certain atmosphere, that's what you're saying? That's if
what
we
I'm
have
saying, I'm talking about
3,000.
nitrogen now.
Okay, you are.
Nitrogen.
And the nitrogen would leave
The-
so fast it
The
would.
nitrogen would fizz out of solution so rapidly it would do damage. You see, we're absorbing the oxygen so into the cells, and so it's not, plus the value isn't as high, but that nitrogen is 600 at 1 atmosphere, and as we start breathing at 5 atmospheres or some outrageous pressure, the number goes way up. As long as you got that pressure holding it in solution, that's okay. But that's why you have to put someone in a compression chamber, a hyperbaric chamber,